Hello, everybody, and welcome to episode 4 of my video series in which we program a video game from scratch, from beginning to end, in the beautiful C programming language. So, let's do a quick review of what we've done up until this point. I've got our solution open here, game B. You can see I've got 4 functions. There's our win_main, there's our main window procedure. We've got our game is already running function that we created last time, and we've got our create main game window function that we created last time. So the first thing I want to do is, remember before I was sort of going back and forth about this message loop, and I felt like something was wrong with it, and I knew I wanted to change it, I just wasn't quite sure how. And I thought about it, and it occurred to me. It just occurred to me today. Oh yeah, this message loop is insufficient for our purposes, and the reason why is because this function, this get message function, it blocks until it receives a window message. As you recall, the get message function, it sits and waits for a window message to come into the queue for our main game window, and that window message may be the user clicked a mouse button, the user pressed a keyboard button, the user clicked the minimize button, the user is resizing the window. All of these different things come into us as window messages. They come into our message queue. Anyway, this function will sit there and wait and halt the execution of our thread. That's what I mean when I say it blocks. It halts the execution of our thread, waiting for a window message to come in. So if you think about that, we in the regular Windows world, that works just fine, because say you have a program open like calculator. Let's say you have an application open like this, and if it's just sitting there, you don't necessarily want for Windows to be repainting the entire user interface as fast as it can. That would be silly. That would use up all of your CPU, because your computer would be doing nothing but redrawing the GUI for calculator as fast as we possibly could. So what's better than that is to actually not do anything and wait for window messages to come in. Wait until we have something to respond to. For example, notice when I hover over a button, you get these cool little graphical effects, those little shinies, and it highlights buttons as I mouse over it. It's because these mouse overs, every time I move the mouse, it is throwing window messages at the calc.exe app, and the calc.exe app is then handling all those window messages in a way that causes all these cool, pretty effects. But if we're not doing anything, then we don't want the calculator app to waste any time redrawing its GUI or doing anything really. Back to our game, though, that the reason why that doesn't work for our game is that I want our game to keep running even if the user is not pressing any keys or moving the mouse or doing anything. Imagine, if you will, if we used a message loop like this, where your character would be standing there on the screen, and then you press the right arrow to move him to the right, and like it draws a few frames of animation, and then it stops, like the entire game freezes, and it waits for another message, or another window message to come in to the message queue. That would not work at all. Completely not work at all. So what we need is a constant, steady message loop, a constant, steady main game loop, actually, is what I should say. And to accomplish that, what I think I'm going to start is I'm going to start by declaring a global variable, and we're going to make it a Boolean, which is a true or false type of value. And in C, in old school C, that's 0 or not 0. So let's go ahead and make it main game is running. So a couple things to note is, so I just declared a global variable, and what that means is that, see how it's not, this variable that I just created is not in the scope of anything. It's outside the scope of all these functions, and what that means is it's accessible by any function in this entire program. In contrast, if we have a global variable like this, if we go to our main window proc function and we look here, this is called a local variable because it's defined within the scope. It's declared within the scope of the main window proc function. That means that only the main window proc function can see this variable. It's a local variable. So back up here, this is our global variable. Anyone in the program, any function in the program can see it. Any function in the program can also manipulate it. The second thing is, notice I put a lowercase g. That's just to remind me that it's a global variable. A lot of people do like g underscore. A lot of people do capital G. A lot of people do all sorts of weird things, but what I like to do is just prefix it with a simple lowercase g, and that's it. The last thing to note about this global variable is that global variables are guaranteed to be initialized to 0 unless you initialize them otherwise. So for example, I don't have to do that because I'm setting it equal to 0. It's redundant because global variables are guaranteed to already be initialized to 0. So I don't need to initialize it unless I intend to start it off as something other than 0. So I'll just leave that like that. So now here we are in our win_main function. Let's get back down here to the loop, and I'm going to say right before we start our main game loop, I'm going to set our global main game is running. Actually, that's a stupid name. Main game is running. I'm only making one game, so what's a main game? I don't know. I'll just do g game is running. How's that? All right. So right before we start our message loop or main game loop, I'm going to set this to true, and this lets everyone know, okay, our game is now running. So now I've set this while loop to say we're going to keep looping through this while loop as fast as we can, as long as the game is running variable is true. And you could either type it like this, or you could type it like that. If you haven't picked up on it by now, the 2 equal signs is a comparison operator. It's how you evaluate whether something is equal to something else or not. In contrast, a single equal sign is an assignment operator. It's how you set your variable to a certain value. So you can write it like that, you can write it like that, you can also write it like that, and let me erase the first part. So you could put true on either side of the equal sign. A lot of old code looks like this because if you put yourself in the habit of putting the constant on the left side of the comparison, then it keeps you from making like an accidental mistake like that. Like this is a very common mistake of just writing 1 equal sign instead of writing 2. And if you put the constant on the left side of the equal signs of the comparison, it won't let you, the compiler won't allow you to make that mistake because you can't assign a new value to a constant. Like true is equal to 1. I can't make it equal something else. So this statement is not, this expression is nonsense, and that's why the compiler tells me that expression must be a modifiable L value. So anyway, I don't really like to do that. because I just think it kind of like looks silly. So, you know, I basically just trust myself to always write the double equal signs when I mean to. All right, so we have our loop here, and this loop will keep running until we switch that off. So what I'm going to do is I'm going to go down here to our main window proc, window procedure, and I'm going to say that when the user hits the X button, recall when the user hits the X button on our window, it sends this WM close message to our message queue. In here, then we post a quit message. It tells the application to actually quit, stop running. And it breaks out of our little loop we had going here. What I'm going to do is I'm going to set G game is running equals false here. So this tells me to break out of this loop. I'm going to then take this, cut it out, and let me check my notes real quick. That is not what I want over there. What I want is something more like this. Okay. Peak message. Peak message is very similar to get message, except peak message doesn't block. Peak message, as the name implies, it basically takes a look at our message queue, and if there's nothing in it, then it keeps going. If there is something in it, then I can dispatch the window message appropriately. So let's see. If I open parentheses here, it tells me what I need to supply. The message, which is going to be our message right there. It's going to be, we need the handle to our window, which is, we created it up here. Aha, we have another problem. So in order for peak message to work, I need the handle to our window. And since our window is created in another function, I don't have access to the window handle that was created in this function right here. So what I need to do is the easiest solution is simply to make it a global. So I'm going to do handle G game window. And that will be null by default, or 0 because it's a global variable, so we don't have to worry about initializing it. Now what I'm going to do is I'm going to go to create game window, create main game window. I'm going to go down to this function. There is our window handle, but it's a local variable, so it's only accessible from within the create main game window function. So what I need to do is I need to change this to G game window. There we go. And I'm going to go back up here. I'm going to delete this local variable. Go back down here, copy, paste. I think everything else is appropriate. Okay. So now we have made our main game window handle a global variable. So now we can supply it in that function right there. Let's see, the message filter, we're not filtering the messages. You use those parameters if you're filtering for a particular type of window message, which we're not. And then finally, this last parameter is basically saying if you want to call peak message and actually just look at the next window message in the queue, but don't don't remove it from the queue, you can actually you can not set that. But if I set this PM underscore remove constant, this parameter here basically says if peak message looks in our Windows message queue and finds a message, then I'm going to remove it from the queue, dispatch it to our window proc, and keep it moving. Just keep it moving. All right, and then all I need to do is dispatch message. What do you supply here? The message, yeah, message. Okay, now let me go back here and put an A right there. Okay, so now we have nested while loops, which means as long as my game is running, we're going to keep running this. And then this says as long as there are messages in the queue, we're going to keep dispatching them to our window procedure until there are no messages left. And then we're going to continue and run whatever else I have in store inside this while loop, and then do it all again. And we're going to keep going forever and ever as fast as we can. So what else do we have to do? All right, this is going to be our main game loop, and essentially what we're doing here, I mean, I'm going to do what? Process player input. I'm going to do that, right? So the user is going to be, he's either going to be pressing keys on the keyboard, or he's going to be pressing buttons on a joystick or a gamepad. So I have to process all those things. And then what am I going to do? I'm going to render frame graphics. So that's pretty much all I have to do. And basically this while loop right here resembles one frame. So let me go ahead and close this. Okay, so yeah, that while loop basically resembles one frame. I would say video games, you typically want your video games to run at 60 frames per second, right? It's pretty normal, it's pretty standard. You know, there are some games, I remember when Assassin's Creed, I think Odyssey came out, because the graphics engine was not capable of pumping out 60 frames per second on any like common home gaming PC that anyone had at the time. It basically always ran at 30 frames per second, and that made the motion like a lot more jittery, and people didn't like it because people were really starting to get used to 60 frames per second. Like on the old Xbox and the old PlayStations, they were limited to 30 FPS because their hardware wasn't powerful enough to maintain 60 frames per second. But it makes a big difference to the player. The movement, the motion is a lot smoother at 60 frames per second. So anyway, the developers of that Assassin's Creed game, they wrote this article about how, you know, they meant for it to run at 30 FPS because 30 FPS was more quote unquote cinematic, which obviously was bull. It's not, 30 FPS is not more cinematic. It's simply that their graphics engine couldn't run at 60 FPS. Anyway, so I think we're going to strive for 60 FPS, and I'll show you why at some point why we can't get exactly 60 FPS. All we can do is get really close, hopefully imperceptibly close. So let's see, what's the next thing? Okay, what do I want to do next? Let's just start with this function. We obviously have not made that function. We need to make it, don't we? So let's just do that. So essentially, these functions, such as the process player input function, they're basically just functions that I intend they will never fail. I'll just assume that these functions never fail, so I am not caring about their return values. I'm not checking their return values, so that's why I return void. And I don't think I need any input parameters. If I do, if that changes, then we'll change the declaration. But let me go ahead and make this function. I'll go ahead and scroll the bottom and make a new function there. And now we can go back up here to WinMain, take out these comments, and now that's a real function. So our process player input function is going to get called every frame, so 60 times per second, which is 16.67 milliseconds. Every 16 milliseconds, this function is going to get called. Let's do this. I want to make it so if I run this, let's make sure it still works, by the way. I can still size it. I can still minimize it. So yes, it looks like I'm processing window messages just fine. Looks like it's working just fine. The CPU usage, if you look over here, the CPU usage, it looks like it's pretty high. And it looks to me like it's at about, see, hold on a second. I wonder how many. I'm going to look at Process Explorer here. Yeah. CPU is really high. And you can see I've got 4 CPU cores here. And I don't know, this just feels really high to me. So let me sort this by CPU, see what's taking up the most CPU. There we go. OBS and our game. So despite the fact that my game does nothing, it's just a blank window, even still it's taking up almost 25% CPU, and that's because I have 4 cores and it's taking up essentially 100% of one core, because the game is single threaded right now, which means the most it can possibly take up is 1/4 of my entire CPU resources, because I have 4 CPUs, but this game only has 1 thread, and the thread can get scheduled on any of those 4 CPUs, and basically it's just running this loop as fast as it can. This loop right here, it's running it as fast as it can, and therefore it ends up taking up around 25% of my total CPU, which is 100% of one entire thread. Hopefully that makes sense. Anyway, that is obviously not desirable. Like, no one should ever write a Windows app that sits here idle doing nothing and takes up 100% of a 3 gigahertz CPU. That's ridiculous. So at some point, what we're going to end up doing is we're going to end up putting some sort of sleep in here. So I'm going to go ahead and do that. So there's the sleep function. Literally just puts the thread to sleep for a specified number of milliseconds. I'm going to go ahead and put sleep 0 here, and I'm going to close my game. So a lot of people have strong opinions about the sleep function, and a lot of people say, if you're ever going to call the sleep function, you should never call it except with a parameter of 0 milliseconds. And what that means is, and again, all you have to do is look up the sleep function on MSDN on the Microsoft documentation, and it explains all these things that I'm saying. But if you call the sleep function with a parameter of 0 milliseconds, it's basically telling this thread to basically yield to any other thread on the system that wants to run. So that way I go from hogging the entire CPU, or one out of my four CPUs, from hogging the entire CPU to now I get to the sleep function, and then I automatically say, does any other thread want to run on this CPU? If so, I let them go, and then I resume. So there's a problem with that, though. Is there's two problems with this for our purposes. Number one, I'll go ahead and show you problem number one. The first problem with doing this. If I run it again, here's our little window, and it's doing the same exact thing. It's kind of not doing anything. Notice that if I look at my CPU graph, I still spike out at 100% most of the time. Every time you see one of these little dips, it's because some other thread got to run for a tiny little sliver of time. But 95% of the time, I still get to run because nobody else happened to want it to run on the CPU at that moment that I called sleep. So I ran again for another iteration of the loop. So this still doesn't really do anything for me, this sleep zero. I mean, it does allow other threads to run if they really want to. If my computer is in a really CPU starved situation, but it's still unacceptable for my little do nothing application that does nothing to be sitting here and idling at 100% almost all the time, 100% CPU. Still unacceptable, so not going to do it. The second problem with doing that, with doing sleep zero, is we have no idea how long the sleep is going to be. If I yield execution to another thread, I don't know how long that other thread is going to run. I have no idea how long that other thread is going to run. I'm not sure if maybe multiple other threads are going to run before my game, gets a chance to run again. That is also unacceptable to me because I need to have some amount of predictability in how fast my game loop is going to run, because if I don't have that predictability, then I won't have smooth graphics. My graphics are going to be super jittery, and it's going to be a total disaster because I need that fluidity of, I need 60 FPS, and I need it to be as close to 60 FPS 100% of the time, as often as possible. So I'm going to go ahead and tell you that this is probably not going to happen today on this episode, but in the future we are going to have to make that. We are going to have to make that happen at some point. The big issue with this sort of timing in Windows is that we're basically trying to achieve real-time results with a non-real-time operating system. Windows is not a real-time operating system. You have threads that are running and they're constantly interrupting each other. You have APCs and DPCs constantly executing who knows what, some things that are completely unrelated to your application, but they're using your threads. And you basically you have no way of guaranteeing that exactly 16 milliseconds has elapsed by the time I get all the way back through the loop again. The best I can do is get really close. So anyway, to solve problem number one, problem number two is much harder to solve, but problem number one is really easy to solve. I'm basically just going to replace sleep 0 with sleep 1. Now, when I sleep with a parameter of 1, that's 1 millisecond, I'm actually not going to sleep for 1 millisecond every time this loop we go through this loop. But I'm going to just run it just to show you the vast difference that it makes just sleeping for 1 millisecond. You can see that now my CPU usage is practically 0. I mean, every once in a while you'll get just a tiny little bump of something, But for the most part, I mean, CPU usage is like 0.0 something percent. It's very low. And that's just with the sleep of 1. If I were to sleep, more, it would be I would get even less CPU usage, because now I'm going to sleep for 20 milliseconds every single frame. Of course, we know that is not acceptable, because we need every frame to complete within a maximum of 16.67 milliseconds, or else we won't be able to hit our 60 FPS target. So anyway, I'm just going to leave that at sleep 1 for now, knowing that we're definitely going to have to revisit this and do some tuning, because yeah, basically our sleep can't be too high and it can't be too low. Okay, next thing I want to do is I want to process a little bit of player input, and I want to start by making it so that when the user hits escape on the keyboard, I want to make it so that when I hit the escape key on the keyboard, like I'm doing right now, it closes the game. It exits the entire application. So what I'm going to do is I'm going to close that. Now, process player input. Like I said, I'm going to put all of my everything that I do in this game to respond to player input, whether it be keyboard or gamepad or whatever. I'm going to do it inside of this process player input function. So let me go down here to process player input. Okay. What I'm going to do is I'm going to make a variable, and I'm going to call it, and I don't know, I'm just going to start with an integer, because I don't know what type of variable I need yet. I'm just going to start with an integer by default. I'm going to name the variable escape key is down. And I'm going to assign to it the result of the get async key state function, which is a function that takes as an input a virtual key code, and I'm going to do vk_escape. Okay, so what get async key state does is, well, just like it sounds, it tells me if the key that I specify right here is pushed or not. I'm going to go ahead and look up this function. Let me look it up over here. Get async key state. And it takes me to docs.microsoft.com. Determines whether a key is up or down at the time the function is called, and whether the key was pressed after a previous call to get async key state. Now, the function actually returns a short, which is half of an int. It's half of an integer. All right. If the function succeeds, the return value specifies whether the key was pressed. If the most significant bit is set, the key is down. And if the least significant bit is set, the key was pressed after the previous call to get async key state. However, you should not rely on this last behavior. Okay, I won't. So essentially what that just said is, with this most significant bit and least significant bit stuff, what it means is, this is going to be true. It's going to return true if the key was pressed down, and it's going to return false if the key was not pressed. So first, let's change this to a short. And at this point, it might be time to talk about a little bit about data types. I've been using things like int and short and things of this nature for a while now, and I've never really explained what they are, have I? So to do that, I better get something open. Well, here. Let's see. Can I? No, I can't do this. Well, that's pretty annoying. Let's just use regular notepad. Okay. Data types in C. Lesson of the day. Okay. So when I type int, what that is, it's short for integer. And if I'm assuming I'm basically speaking to people who are not very familiar with programming. But even if you're not familiar with programming and really not very familiar with computers at all, even then, I think just about everybody knows that the basic, most fundamental, most atomic unit that computers operate in, the language, is ones and zeros, right? Binary code. Just about everybody knows that. So an int, or an integer, is basically so that's 1632. So this is basically an integer right here. This is 32 bits. Each little zero, and I only space them out, so I could group each one of them by 4 just for convenience sake. Each one of these little zeros is a bit, and it's a switch that can be flipped on and off. That's what a CPU is, right? It's a little chip of silicon containing literally billions of microscopic electrical switches that can be flipped on and off at just a mind-boggling frequency. So you do that fast enough, you can make all sorts of wild things happen. So in any modern machine, like anything that runs Windows or Linux, or almost any machine, an integer these days is 32 bits, which we have right here, 32 bits. Now, if I took this one bit right here and flipped it to a 1, that becomes the number 1. This is the least significant bit because it's the smallest. Now let me copy this again. Let me copy this. Now if I were to flip the second bit on and the first bit off again, this is actually the 2 position. So the number is now 2. Let me go ahead and write this like this. Okay, that's the 1 position, that's the 2 position, that's the 4 position, this is the 8 position, this is the 16 position, this is the 32 position. That's not very readable, is it? But I guess I'm going to keep going with it. This is the 64 position. And finally we have the 128 position. Looks right to me. So what I'm saying is, if I flip this, it is equal to 1. If I flip the second bit, then I add 2 to whatever other number I have. So let's say if I flip both of these bits, if I flip the bit in the 1 place and the bit in the 2 place, then I add those together and I get the number 3. Now if I flip just the bit in the 4 place and flip that bit off, then I get a total of 4. And if I flip on, let's see, I need 4, don't need 2, I need 1. So 4 and 1 together equals 5. Does that make sense? So this is 8 bits. These two quads put together, those two together, that's 8 bits. The highest, if you kept going with this, sequence that I've got going here, and I'm not going to go that far, but like 4 and 2, and then flip off that, we get 6, right? And keep going and keep going and keep going. Once I use up all 8 bits, like this, 1 1 1 1 1 1 1 1, the most that I could possibly count up to is 255, right? Because 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. Does that make sense? That's our first 8-bit. Now, what if we wanted to count up to a number greater than 255? Because that's a pretty common thing to want to do. If you want to do that, you have your two options are basically do everything in multiple operations or open up more bits. So if I were to open up, say, 16 bits, now I can count up to a much larger number, right? Because let's just keep going. We got see that this bit, this 9th bit here is 256, and then the next bit is 512, like so. So like I add that bit there, and I just added 256 more. I flip that bit on, I've added 512 more, and I keep going and keep going all the way out there. So once I finally, let's erase these two. Once I finally filled up all, or flipped on all 16 bits, I can count up to a maximum of 65,535, I think it is, pretty sure. And PowerShell can do this. I think uint 16, and the max value 65,535. 65,535 is the highest you can count up to using 16 bits. Now, to keep going, if I unlock all the rest of these bits and I have 32 bits, I can count up to 4.2 billion. Uint 32. Yeah, it's 4.29 billion, so about 4.3 billion. Like the age of the Earth, I think. No, I think the Earth is like 13 billion or something. I don't remember. No, age of the universe, 13 billion. Earth, 4 point something billion. It doesn't matter. There's one other really, really important thing to note, though, is the difference between signed data types and unsigned data types. There comes a time where we may want to express negative numbers. Notice how everything here has all been about positive numbers. What if you want to express negative numbers? Well, in that case, I'll take my 8-bit example here, negative 127. So what happens is if you tell the C compiler that, hey, this is going to be a signed data type, then what it does is it allocates the same number of bits. You still get 8 bits, but it uses this last bit over here as the sign bit. It's either positive or negative depending on which way the sign bit is. Honestly, I don't remember if it's 0 or 1. All I know is the sign bit is, if it's 0, then it's positive. If it's 1, then it's negative, or maybe the other way around. But you get the idea. It's one or the other. You flip this last bit over here to determine whether the number is positive or negative. The downside of that is that you lose this most significant bit over here. You can no longer count as high. See, I've taken 128 away from the highest number that I can count to, because this bit right here is reserved for the negative sign, essentially. What else? So I think that about covers that, and I hope it's clear. It's pretty simple, but that brings us back to this. So a short As you can see, if it's blue like this, it's built-in. It's like the compiler just intrinsically knows what it is. It's just like you don't need any headers, you don't need any library. It's just like the compiler just intrinsically knows what this data type is. Same with int. Same with float, which is super interesting. Same with decimal, or it's not decimal, it's double. Those are really interesting data types that you use to express decimal numbers, like 3.14, 159, 265, whatever. Yeah, that's what these are for. So on other platforms, it's possible that an int may not have always been 32 bits. Like like I said in episode 1, that long time ago we used to use 16-bit computers. I don't know if an int was still 32 bits way back then or not. But you also might find differences if you go to like some embedded systems that use different sizes for their data types. But if you're on Windows or any sort of like modern PC sort of platform, it's safe to assume that an int is still going to be 32 bits. Even on a 64-bit computer, an int is still 32 bits. I'm going to look up C data types, by the way. And I'm going to go to Wikipedia. Yeah, so a char a char is the same thing as a, well, okay. A char is 8 bits. And remember when I showed you that ASCII table, the literal character A translates into the number 97, and 97 just happens to be small enough to fit in 8 bits, and a char is 8 bits. If you look at the byte A, if you look at this type, see how it's green? That's because it's actually type deft to an unsigned character. And I think when it's green, that means it's defined in a header file. Pretty sure this is defined in Windows.h. So it's not this byte data type is not built into the C compiler. It's actually defined in Windows.h as this unsigned char. So yeah, but it's the same thing, right? It's char A equals A, and we could do unsigned char A equals A. Of course, you can't have two variables that have the same name, can you? And we can keep going like this. We can make an int, we can make it unsigned, we can make all these things unsigned. Maybe not the floats, but definitely the shorts. Alright, back to C data types. Okay, short and short int are the same. A short signed integer type capable of containing at least negative 32,000 to positive 32,000. Thus, it is at least 16 bits in size. Notice the phrase "at least." So, like on certain platforms, it could actually be more than 16. So, I guess the idea is that the short is guaranteed to be at least 16 bits in size. You have the int. It's signed by default, but you can make it unsigned by typing this little unsigned keyword. See, here it is. It says it is at least 16 bits in size, but I don't know what platform that's applicable to, because on this platform, on Windows, it's 32 bits. I'm going to run to cursor. I have errors. I can't have a redefinition. These can go. All right, let's try that again. All right, locals. Yeah, here's my C, my unsigned integer C, unsigned int. If I do if I type in here size of C, it tells me 4. It's my unsigned integer C is 4 bytes. A byte is 8 bits, so it's 32 bits. So I'm going to stop that now. Now the weird thing is like there's also a long data type, unsigned long D equals. And if I run to cursor here, then what happens? Well, size is size of D. I gotta type it correctly. Size of D. It's also 4. So on this platform at least, integers and longs are the same size. So there you have it. And this syntax here, this is just another way of writing numbers. It's called hexadecimal. I guess since we just did data types, we better do a lesson on hexadecimal. But maybe next time. Maybe we'll do that next time because we're running pretty low on time, and I want to go ahead and get this taken care of. All right. So anyway, back to get async key state. Returns a short. So we're going to assign it to a short. I'm going to say if escape key is down, then okay, so what I want to do is if the user hits the escape key, I want to send our own window a window message. I want to send it the WM quit window message. And if you recall, we specifically configured our main window proc. Oh, I'm sorry, the WM close window message. We process the WM close window message, so I know exactly what will happen whenever I send myself the WM close message. Is I'm basically going to turn the game off and quit, and then exit the program. So the function to send a message to yourself is probably send window message, send notify message, send message. Okay, let's try that one first. And we're going to use the A for ASCII. Come on. Okay, now we need to specify a window to send this message to. We know that's going to be our main or our game window. Now, what is our message going to be? WM quit. And then, do we need wparam and lparam? No, I don't think so. These are just extra parameters that you can send along with your window message in case you want to pack some other data in there for your window procedure to do something with. But I don't think we need any additional parameters, so I'm just going to pass 0 in place of those. So now I think what will happen is I think when I press escape, the window will close because it receives a WM quit message. So let's try it. Okay, here's my window. And if I hit escape, oh, it doesn't work. It didn't work. Okay. So let's see here. Oh, no, that's not it. Oh. Hold on, let me check my notes over here. I really feel like that ought to have worked. I'm bummed out that it didn't. Oh, wait. Wait. Damn it. I sent it WM quit when I meant to send WM close. Hold on. Let me send the WM close message instead of the WM quit message. Let's see what happens now. Okay, game is running. Here's our little game. Hit the escape key. Boom, it works. Okay, so now we have keyboard input working. And we're obviously going to elaborate a lot on this, but we already have the basics. So, I feel like we got a lot done today. How much? 56 minutes. I figure since I go over, I've gone over in the past 3 videos, it would make sense to go a few minutes under this time, I guess, because I don't know if I have enough time to really start into anything else, because the next thing that we have to do is, let me go back to WinMain. Yeah, here's the big guy. The next thing we have to worry about is rendering frame graphics, and I think that's going to be a really cool episode. So stay tuned, and if you have any comments or questions, please post them in the comments section, and I'll answer them. I may even talk about them in the next episode. You can also find me on Twitter at Joseph Ryan Reese, and I guess that's it. So yeah, like, subscribe, and catch you next episode.